Hello everyone from the world of industrial automation. My name is Artem Melnik. I'm a software engineer with 15 years of experience in developing firmware and software for programmable logic controllers and integrating CODESYS runtime into this firmware. Let's develop an automated control system for an industrial dry heat sterilizer. All the devices mentioned are connected to each other through a router that has internet access. Let's take a look at the structural diagram of the equipment connections. As we mentioned earlier, instead of a real sterilizer, we're using an emulator. When it comes to a Linux-based PLC, the manager is the PLC operating system's task scheduler, and the workers are the PLC processor cores. If the time spent executing your code is greater than or equal to the task interval, it means the processor core won't be able to start executing the next tasks. That's why it's important to make sure that the time your code takes to execute on the processor core doesn't exceed the task interval of your control algorithm. PLC tasks that provide communication with higher-level systems, such as cloud, HMI, and SCADA, are configured as lower priority tasks, while PLC tasks that handle communication over industrial buses with I/O modules and field devices, which also provide PLC redundancy, as well as user tasks that control field devices, are considered high priority, or in other words, critical tasks. Now, our prototypes support at least two models of sterilizers with different characteristics, such as the type of thermal insulation material, the volume of the sterilizer chamber, the number of heating elements, and the number of internal temperature sensors. Let's go over the changes in our emulator project. The first thing we did was rename our program. To rename it properly, we use a mechanism called refactoring. To do this, in the device tree, we select our program, right-click on it, then choose the Rename option under the Refactoring section, select a new program name, and click OK. If we didn't use this mechanism, we would have to manually change this expression to this one everywhere. There are a lot of such places. These include various visualization components, the program's source code, and different files where the old program name is mentioned. Thanks to this mechanism, the CODESYS environment does all this for us. Secondly, we introduced a list of constants, the maximum number of internal temperature sensors, the maximum number of external temperature sensors, and the maximum number of heating elements. Next, we replaced the value 6 in the variable declarations and in our program code with our constants. This applies to the array of sensor types, sensor inertia or time constant, types of heating elements, and the maximum power of the heating elements. We also replaced the value 6 in the arrays for external temperature sensor readings, internal sensor readings, analog output signals for transmitting internal temperature sensor readings, and in the array for the current power position of the heating elements. As you remember from the previous video, we reduced the number of lines in our algorithm by adding an action. Let's go to this action. Next, in this action, we replace the value 6 with the corresponding constants. Also, in the rest of the emulator algorithm, we replace the number 6 with the appropriate constants. As the next step, we duplicated another functional element of our program. Now we have an exact clone of our program, where, through refactoring, we also rename a program. This approach of duplicating source code has its drawbacks. What if we need to support not just 2 models, but 100 models, for example? That would mean we'd have to duplicate the code 100 times. And with any change to the algorithm, we'd have to make the same update in each of those 100 instances. Let me know in the comments if you know how to avoid duplicating source code. After that, we added a call to the second program in our main task using the Add Call button. The next step was to rename our visualization using the refactoring tool. After that, we duplicated the visualization file. And since we changed the name of our visualization, we need to enter the new visualization file name in the corresponding components of the device tree for the target visualization. And we need to do the same for the web visualization. The first visualization will display the first sterilizer model, and the second visualization will display the second sterilizer model. Let's go back to the first model. The added components are controls for the number of internal temperature sensors and the number of heating elements inside the sterilizer chamber. Furthermore, we've also incorporated new configuration settings for extra internal temperature sensors and supplementary individual heating components. In the first visual control component for the number of internal temperature sensors, in the variable field, we link the variable for the number of internal temperature sensors and set the minimum and maximum values. In the second visual component, SpinBox, in the variable field, we link the variable for the number of heating elements and also set the minimum and maximum values. In the next component, we link the second element of the array to the variable field, which corresponds to the second internal temperature sensor. In the deactivate inputs field, we wrote a logical expression. If the number of installed internal sensors is less than 2, then the control element will be unavailable for entering a new value. We entered almost the same expressions for the third temperature sensor, the fourth temperature sensor, the fifth temperature sensor, and the sixth temperature sensor. For the inertia or time constant settings of the third, fourth, fifth, and sixth temperature sensors, we repeated the previous steps. We performed similar actions for the settings of the additional heating elements. Next, we added a button, and for the mouse click event handler, we linked a function to change the visualization, where in the assign field, we selected the visualization of the second sterilizer model. Now, let's switch to the second visualization, which corresponds to the second sterilizer model, and you'll see all the same settings that we duplicated. But for this button, we added a mouse click event handler and linked a function to change the visualization, where we switched to the visualization of the first sterilizer model. And all the other components of the visualization for the second sterilizer model, if we look at the corresponding fields in the properties, we'll see that the prefix here is not 1, but 2. And accordingly, for each element, we change the prefix as needed. In the settings of our module, we also configured 2 more analog outputs to generate a 4 to 20 milliamp current for transmitting the readings of the internal temperature sensors of the second sterilizer model. On the I/O mapping tab, we also linked the corresponding variables, but this time from the program with the prefix 2. We increased the number of holding registers to 12. Next, on the I/O mapping tab, from the first program, we linked all 6 elements of the array for the current power position of the heating elements for the first sterilizer model. And likewise, from the second program, we linked all 6 elements of the array for the current power position of the heating elements for the second sterilizer model. Now, let's go over the changes made to the automated control system project for the sterilizer fleet. We renamed the file of our main program, then duplicated it, added the call for the second program to the main task, renamed our visualization, and duplicated it as well. We also added a button to switch to the second sterilizer model, and added a button to switch back to the first sterilizer model. In the first program that controls the first sterilizer model, we added 2 variables, an array of internal temperature sensor readings and an array of the current power levels of the heating elements. In the first expression, we assign the reading from the first temperature sensor to the current temperature variable, while in the second program, we assign the average value of the readings from the 2 temperature sensors. Let's return to the control algorithm for the first sterilizer model. Since the first model uses only 1 heating element, we assign either 1 or 0 to the first element of the array representing the current power position of the heating element, depending on the conditions. In the second program, we assign either 1 or 0 to both the first and second elements of the array. In the settings of the analog input module, we configured 2 more analog inputs to operate in 4 to 20 milliamp current measurement mode. In the I/O mapping tab, we linked the first channel from the first program to the first element of the array, which is responsible for the readings of the first internal temperature sensor of the first sterilizer model. And for the second and third channels from the second program, we linked the first and second elements of the array for the second sterilizer model. And in the Modbus TCP slave device, we increased the number of registers in the request to 12. From the first program, we linked 6 elements of the array to the corresponding registers for the first sterilizer modification, and to the remaining registers from the second program, we linked 6 elements of the array representing the current power position of the heating elements for the second model. We didn't make 2 separate requests, one for the first and one for the second sterilizer model. Instead, we made just one request, which directly affects the response time for controlling the heating elements. If we send all 12 power values for the heating elements in a single request, we'll get a faster response time for controlling these heating elements. But if we use 2 requests, there's a network delay, and because of this delay, the response time for controlling the heating elements will be slower. To enable interaction between cloud and the second sterilizer model, in the symbol configuration, we marked the same variables as we did for the first sterilizer model, but this time for the second software component, which we duplicated. Let's see how this looks now in cloud. Now we can see that a second software component for monitoring and controlling the second sterilizer model has been added to cloud. So now, cloud supports 2 sterilizer models on a single SPC210. In the next video, we'll get acquainted with the concept of libraries and improve our prototypes. Our channel has the exclusive right to offer a 35% discount promo code for SPC210 and input-output modules from akYtec. To get this promo code, just send a private message with the text promo code to any of my contacts, melnikartemg@gmail.com, WhatsApp, or Telegram at the phone number +1 904 505 6665, and I'll send you the 35% discount promo code in a reply to your contact. You need to apply it to your card in the special promo code field. And here's another nice surprise for those viewers who purchase SPC210 and send me the device's serial number in a private message. I'll provide all the CODESYS projects used on our channel for free. And don't forget to subscribe to our YouTube channel so you don't miss the next videos, and give this video a like if you enjoyed it. That's all for now. See you in the next video.